All right, in order for us to understand simple machines and mechanical systems a little bit better, we have to learn yet another physics concept. And this physics concept is called torque. Torque. You may already have an idea that torque has something to do with twisting or spinning. And that's precisely what torque is. First, let's talk about what it is in general, and then we'll talk about how we deal with it sort of mathematically. So I want you to envision a big long piece of wood, a 2x4, something like this. In the center of the 2x4 there would be a point we could call the center of mass. The center of its mass, right? The balancing point. If you put your finger on that spot, you could balance, or your arm, you could balance the 2x4. And so that's the center of the 2x4. Now, up until now, we've been looking at forces, right? So let's say I push on the end of this 2x4 and I push it here. As long as my force is lined up with that center balancing point, then what will happen is the whole 2x4 will move this way. And likewise, if I take that same 2x4 and I push, even if I push down on it this way, right through that center point, then the whole 2x4 will just move down. But what would happen if instead of pushing towards that center line, what would happen if I had a 2x4 like this with a center here, but instead I pushed over here? Well, we all kind of know what would happen. Instead of the 2x4 moving from one direction to another, or from one position to another, like displacement, instead of being displaced, right? So here, let me draw, just to give you an idea what I mean by that, let me draw on our previous picture, let me just draw this. This 2x4 would, the one that we drew, would be down here after. The whole 2x4 would have moved from one place to another, see? It's displaced. But in the picture we're drawing now, with the force acting on the end, like it is, what we would expect is that the end of this 2x4 would begin to spin around or rotate, and the 2x4 would spin or rotate instead of making a move from one position to another. So this is displacement over here, moving from one place to another, and it can only be caused if the force that you're applying is lined up with the center of the object's mass, or the balancing point. If you push with a force that is not on the balancing point, like we did here, we can cause objects to spin or to rotate. And this type of force that's applied that causes a rotating spin is what we call torque. Torque. So torque is very much like a force. The only difference is it's a force that's not applied through the center of an object, the center of its mass. Okay? And if we use uniformly shaped objects that are nice and even, like a 2x4, then the center of mass is usually in the center of the object. But it doesn't have to be, right? Just to give you some idea about center of mass, if you had an object, let's say you had something at home that had a nice wooden handle, right? Like a pot. But the pot had metal here. Well, the metal is more massive than the wood. And so the center of its mass might not be right in the center, which you'd expect to be sort of here, but it might be closer to one end. It might be over here because of the heavier part, the more massive part that's towards one end. So it doesn't have to be in the center for weird shaped objects or objects made of different materials or that are not uniform. But for the most of the objects we deal with, like 2x4s and stuff, and as we're learning about torque, we're going to just look at objects whose center of mass is pretty much in the center of the shape. Okay? So that's that. So let's look at our picture again. If we take this 2x4 and we put the center here, and we apply with a force here on the end of the 2x4. There's our force. Well, what we have to figure out is how far away from the center are we actually applying that force? How far is it from here? Now guess what we call that distance? We call it r. And you might say, how can we call it r? Why wouldn't we call it d? Well, I'm going to show you why we call it r. In physics, r and d really mean the same thing. They're both just distances. But this is called r because watch what happens when this begins to spin. When it begins to spin, the ends of the 2x4 or the board will spin around and they will create a circle. And the 2x4 can be thought of at any position in that circle, right? Maybe the 2x4 is here, or maybe the 2x4 is here. As it spins around, in fact, if it's spinning fast, it would look like it was all blurred in all these positions, right? Well, guess what? R is the distance from the center to the end. And it's the same distance from the center to the end, no matter which way 2x4 is pointing in the circle. And guess what it looks like? It looks like the radius of the circle. See that? And so we remind ourselves that it's R, to remind ourselves that torque involves moving in a circle. So that's why we use the R. It's not a big deal. But just remember, it's still just a distance, and it's still measured in meters, and it's simply nothing to get too worried about. All right. The other thing that you need to notice in this picture, with the force being applied at the end and the distance from the center being called R, is that the force is at right angles to the R. Right angles. The R is left and right, and the force is up and down. So if I draw the two together here, just to show you, there's my force, there's my R. They are at right angles to each other. Perpendicular. In order to create torque, you need a force that has some perpendicularness in it, some perpendicular to the R. It's possible that the force could be sort of on an angle this way or this way, and there's ways to deal with that, but we're not going to worry about that just yet. We're going to worry just looking at forces that are perpendicular, okay? And it's important for us to remember that. So, the torque is very simply the product of these two things. Torque is a little funny looking T. It's a Greek tau. And the torque is equal to the perpendicular force. And I'll put this little sign here, which looks like a little, well, it's a little perpendicular sign. The perpendicular force multiplied by R, which is the distance to the center. Okay? So this is the little formula that we will use. And this is the picture you should keep in your head right here, because this is the picture that describes what we're talking about. Now, what if the object isn't just kind of sitting there on its own? What if it's not resting on a table? Well, sometimes the torque doesn't have to be from the center. If the object is free and just floating there by itself, like a 2x4 sitting on your garage floor, all right? So here's your 2x4. We're looking down from the top. You kick it over here, it's going to make the 2x4 spin. If you kick it right in the center, it'll make the 2x4 displace or go that way. However, not everything is just sitting there by itself. Let's say you had a 2x4 in your garage, but you put a big spike in the end and you nailed it to the floor. Well, now the center doesn't really matter, does it? I'm going to erase it because the center doesn't matter because one end is nailed down. That means if you put a force here, well, it'll spin. If you put a force here, it'll spin. Even if you put a force very close, it'll spin. The only way it won't spin is if you kick it right on the nail. Then you'd get nothing happening, no spin. And so the distance of the force would be from the nail, not from the center of, there's the first distance, right? Or if this force is that far, or this force is all the way out here. So the distance R is measured from the place that's anchored down. And we call a place that's anchored down the pivot. pivot point, the point at which something will spin. So for a free object that's not tied down, a free object, right? The pivot will be at the center of its mass. The place where the center of the spinning. The pivot is at the center of mass. But for a fixed object is an object that's tied down or hammered down or nailed down or being held. Fixed object. The pivot is the fixed point. All right? The spot that's being held down. Fixed point. Good. And most of the things that we talk about will probably have fixed points in them. So we'll be using fixed objects more often than not. Let's do a little example. A little example, or a couple of examples of how we might work with torque. Okay. Let's say that you are going to try to think of something simple that's not too complicated just yet. All right, let's say you have a pump, and it's a water pump. It's an old-fashioned water pump. It's got a little spout here that the water comes out of, and it comes down like this, a little top, and there's a little thing here, and then sitting on the ground. But there's a handle right here that pivots, okay? And the handle is attached out like this on the pump. And the way, of course, that you pump the water, there's the handle. So what I'll do is I'll remove this because it looks like there. Okay? So what you have to do is you have to take your hand and you have to pump on the handle. So what we're going to do is we're going to push down right here with a force, which will cause the handle to go down. All right? Now, the handle, if we push right on the end of the handle, the distance from the pivot, and I'm using the anchored down end as the pivot, right? Because this part obviously can't move. The distance is going to be 0.4 meters. And we're going to push with a force of 10 newtons on this pump. All right? So let's figure out how much torque are we applying to the pump handle, right? How much torque are we applying to the pump handle? And here comes the water to get the water to pour out. Okay, so at this point, the amount of torque we're applying is equal to the force that is perpendicular to the distance. Well, my force perpendicular is 10 newtons, and my distance is 0.4 meters. And so the answer is 4. And when you multiply newtons times meters, guess what you get? You get a thing called Newton meters. A dot means multiply. So this little dot in the middle here means newtons times meters. So the unit for torque is Newton meters. It's kind of a funny unit, and it's a little bit difficult to understand. Torque is actually quite complicated, and what we're doing is we're just trying to get a simple understanding of it. So that's the unit that you use, Newton meters. And that's how simple it is. It's, you just plug and play. You plug in the numbers you get into the formula, and you can figure it out. Okay. Now, this kind of device is called a lever, isn't it? And torque is very important for levers. And so in our next video, we're going to talk about levers and how torque affects them and how they work. But for today, it's all about just figuring out how to do the torque. So let's do one more example, just for fun. Let's do a more complicated example. Let's see what happens if you have this. You've all been on a teeter-totter. Teeter-totters are examples of torque, because in the middle of the teeter-totter is a balance or a fulcrum, right? Sometimes we use the word fulcrum to describe a balance point. So maybe this is a log or it's something that the teeter-totter is balanced on, and of course the teeter-totter wiggles back and forth. So what you're going to do is you're going to sit on one end of the teeter-totter. So here you are. Here you are with your feet and you're holding on to the teeter-totter, and your mass is 30 kilograms. And you happen to be sitting, if we do our distance thing here, let me move this up just a touch. You happen to be sitting 2 meters away from the pivot point, or the fulcrum, the balance point, which happens to be right over the center. And so what's happening, of course, is you would create a torque that would cause the teeter-totter to sink downwards as you sat on it. But if your little brother sat on the other end, and he's just a little guy, he's only half your age, so sitting over here, your little brother has a mass of only 20 kilograms. But he's going to sit on this side. He's not as heavy as you, is he? He's not going to have as much weight or force. And so in order to balance the teeter-totter, if you both sit the same distance away, you know what happens. You go down, he goes up, and it's no fun. But if he sits a distance that's not the same as you, okay, if he actually sits a little further out on the teeter-totter, okay, and it looks like he probably can't go any further, but you might say, well, how's he going to sit further? I'm going to make this teeter-totter a little bit longer so that that's not a problem. Okay, there. So you're sitting there, and he's going to be sitting a little bit closer to out there. We're trying to figure out how far little brother is sitting, so I'll put it in purple here. We want to know where should little brother sit so that you guys can actually balance, because he's not as heavy as you. Well, we can figure this out by looking at torques. Because what happens when you sit on this teeter-totter is you produce a force downward. And what would that force be? Well, that force would be the force of gravity, or your weight, which is mg. We've learned this before. And so the force that you are applying would be 30 kilograms times 9.8. And that would mean, if you multiply this, 3 8s are 24, 27, 294 newtons of force on the teeter-totter. Little brother is also being pulled by gravity down. His force of gravity is mg, which is, let me rewrite that messy force of gravity sign. It looks like some kind of crazy force of gravity. mg, he is 20 times 9.8. And that's only 196 newtons. If you want to balance, though, if you want to balance, you have to have the same torques. Let's look at the kind of torques you have, first of all. The torque that you have is trying to make the teeter-totter go this way because you're pulling down. But your little brother's torque is trying to make it go this way. So you're making it go clockwise. You're making it spin clockwise. But your little brother is making it spin counterclockwise, the opposite way that a clock goes, clockwise. See that? So the two of you are working against each other, trying to spin this teeter-totter in two different directions. Well, if you want the teeter-totter to balance, then you want everything to balance out. Now remember how we talked about when you have a net force equal to 0, there was no acceleration? Well, if you want a teeter-totter to balance, you have to have a net torque equal to 0. So in order to balance, the two torques, yours and your brother's, must cancel out. The two torques must balance each other. Must balance each other. In other words, the net torque has to equal 0. So you see how this question is a little more complicated, but not too much, because now we can simplify our picture and look at the two torques. All right? So let's just simplify our picture. Dots here. There's the teeter-totter, there's the fulcrum, right? And your force was right here, and your brother's force was right here. His force was 196 newtons, his weight. And your force, I think, was it 294? We better go back and check. Yeah, 294. And you were 2 meters away. So your force is 294. And we didn't know how far your brother was, but we knew that you were 2 meters away, so we're just going to call your brother's distance away r. All right, well, if the net torque balances out, that means the two torques have to be equal but opposite directions. So we can write torque net. The total torque will be the torque of you plus the torque of your little brother. How about that? Y and B. So this is B, and this is Y, U. Well, how can I describe those torques? Well, I want the net torque to equal 0 because I want to balance the teeter-totter. I don't want any spinning. Your torque will be the force perpendicular for you times the distance for you. But your little brother's torque will be the force perpendicular for your brother times the distance for your brother. Got it. Your force is 294 newtons. And your brother's, your distance is 2. Okay? Now, your brother's torque is 196 newtons multiplied by r. We don't know r of your brother. We don't know that part, but we're going to figure it out. Now we have to look at one more thing. We didn't tell the math anything about which way this teeter-totter was being pulled or was being torqued. You were trying to make it go clockwise, but your little brother was trying to make it go counterclockwise. And this is where we get a little bit of a problem. The easiest way to work this out is to use a reference frame, the reference frame for torque. And we all generally accept it. That clockwise is negative and counterclockwise is positive. Now you might say, how come? It doesn't make sense. Why shouldn't clockwise be positive? Well, I'm going to show you, and then we're going to erase it. But look at these numbers and think about vectors. This distance is a distance out this way, away from the fulcrum. But your brother's distance is a distance in the other direction. It's a displacement to the left. If you're multiplying your brother's 294, your 294, let's talk about you. If you're multiplying your 294, it's a downward force, and it would have to be negative, right? If you wanted to tell the math which way the arrow was pointing. Now, the 2 meters, though, right here, is a positive to the right, so it's a plus number. When you multiply a plus and a minus, you get a minus, and you're moving the clockwise direction. So clockwise is minus. If you looked at your brother, he's got a negative downward force also, but his R is to the left. And so you would need a negative number for R, and 2 negatives would make a positive. But we can simplify that. We don't need to worry too much about all that if we just remember what I've written in purple over here. If we just remember that anything that goes clockwise is negative, and anything that's trying to go counterclockwise is positive. So let's look at the torques. Your torque was clockwise, negative. So your answer will get a negative sign. And that's you over here at the start. So you will be 8, 9 and 9 is 18, 588 Newton meters. But your brother's torque is counterclockwise, and he will get a positive sign. And so his torque will be plus, right? So we technically should put the negative in here as well, because your torque is clockwise. And his will be 196 times whatever this RB is. But we don't know what it is yet. But look what happens. Move the 588 to the other side and divide by RB. And guess what? Or sorry, divide by 196 is what I meant to say. And if you do that, it comes out to pretty much 3. Which means your brother would have to sit 3 meters. Oh, look what I did. I wrote R and B. I'm all over the board here. Your brother would have to sit 3 meters away. See, RB, which on the picture was how far your brother is, right here. This was R for your brother, B. So he would have to sit back much further than you, 3 meters away, because that way he makes up for his smaller weight and his smaller force by using a larger distance, and he ends up with the same amount of torque. And that way you will balance out and the board will not move. So this is a very complicated way of looking at torque and how we can use it in a complicated situation. But the easy thing is just using the formula where you have torque, which is the product of the force and the distance. So see how complicated this system, this mechanical system, was much more complicated than the first one that we did. All right, so hopefully you'll be able to calculate torque by using the equation force perpendicular times, right? So the force perpendicular times R is equal to something called torque. And you will also remember that the net torque, well, we could call it, just like we do F net, we can do torque, net torque the same way. The net torque is equal to the sum of all in the individual torques. So in the case that we did it, it was the sum of your brother's torque and your torque. And often you want that torque to be 0 so that the object is balanced or not moving. Okay, so this is really the key to the whole thing right here. Make sure that you can handle that for now. And that's the end of torque. Our next video will take us into the world of levers. And that'll be a lot of fun.